You think you know what radio waves are. They're invisible waves that carry music and voices through the air. Your phone uses them. Your car radio picks them up. They're everywhere. Wi-Fi, cell phones, radio stations, all radio waves. You use them every day, so you must understand them, right? Wrong. Here's a question. What's waving? You say electromagnetic waves. Fine. What does that mean? What physical thing is moving up and down or back and forth? Water waves, you can see the water moving. Sound waves, the air molecules vibrate. But radio waves travel through empty space, through vacuum, through nothing. So what's waving? What's actually oscillating when a radio wave passes through the room you're sitting in right now? You can't answer that, can you? You just repeated words. Electromagnetic waves, but you don't know what that means. You don't know what's moving. You don't know what the wave is made of. You think you understand radio because you can turn on a radio and hear music. But that's not understanding. That's just using a tool someone else built. Let me make this worse. Radio waves are light. Not similar to light, not analogous to light. They are light. The exact same thing. The radio waves carrying this podcast or video to your device right now are identical in nature to the light hitting your eyes from your screen. Same phenomenon, same physics, just different frequency. You don't believe me. You think radio waves and light are different things because one you can see and one you can't. But that's just biology. Your eyes happen to detect electromagnetic waves with frequencies between 430 and 770 terahertz. That's visible light. Radio waves have frequencies between 3 kilohertz and 300 gigahertz. Different numbers, same waves. The only difference is the frequency. That's it. Radio waves are invisible light. Light is visible radio waves. They're the same thing. And if you think that's strange, wait, it gets worse. X-rays, same thing. Microwaves, same thing. The infrared heat lamp at a restaurant keeping your food warm, same thing. The ultraviolet light that gives you sunburn, same thing. All of it, from the radio waves carrying a met radio at 1,000,000 hertz to the gamma rays from radioactive decay at 10 to the 20th hertz, it's all electromagnetic radiation. It's all the same wave, just different frequencies. Your entire concept of different types of radiation, different types of waves, is wrong. There's only one type, electromagnetic waves, and they span a continuous spectrum from incredibly low frequencies to incredibly high frequencies. We gave different parts of that spectrum different names because we interact with them differently. But that's human convenience. The universe doesn't care about our naming scheme. It's all the same wave. So let me ask again, what's waving? You're standing in a room. Radio waves from a dozen different stations are passing through your body right now. Wi-Fi signals from your router, cell phone signals from nearby towers, Bluetooth from your devices, GPS signals from satellites, radio waves from distant stars, all of them passing through you simultaneously, not interfering with each other, carrying different information. What is the physical thing that's oscillating? What's moving up and down millions of times per second as these waves pass through? The answer is going to break everything you think you know about empty space. Let's start with what you think radio is. You think someone talks into a microphone. The sound gets converted to electrical signals. Those signals get sent to a transmitter. The transmitter sends out radio waves. The waves travel through the air. Your radio receives them, converts them back to electrical signals, drives a speaker. You hear the sound. Simple. But here's the problem with that story. How does the transmitter send out waves? What's the mechanism? You say it uses an antenna. The antenna moves electrons up and down. The moving electrons create waves. Okay, how? By what mechanism does a moving electron create a wave? And what is that wave made of? You think it's like dropping a rock in water. The rock disturbs the water, creates ripples. The ripples spread outward. But what's the water in this analogy? What medium is the antenna disturbing? The air? No. Radio waves travel through vacuum, through space. The Apollo astronauts talk to Earth from the moon, and there's no air on the moon. So the waves aren't traveling through air. What are they traveling through? For a long time, scientists thought there had to be a medium. They called it the luminiferous ether, an invisible substance filling all of space, carrying electromagnetic waves the way air carries sound. They did experiments. The Michelson-Morley experiment in 1887 tried to detect Earth's motion through the ether. They failed. The ether doesn't exist. There is no medium. Radio waves travel through absolutely nothing. So what's waving? The electric field and the magnetic field. Those are the things that oscillate. But now I need to tell you what a field is. And this is where your intuition is going to completely fail you. A field is not a thing. It's not a substance. It's not made of anything. A field is a property of space itself. At every point in space, at every location, there's a number, or rather several numbers, that tell you what would happen if you put a charged particle there. Those numbers are the electric field. The magnetic field is another set of numbers at each point, telling you what would happen to a moving charged particle. The field is everywhere, at every point in space, right now, around you, inside you, everywhere. And the field has values, magnitudes and directions, and those values can change. They can oscillate, they can wave. And when they do, that oscillation propagates through space. That's an electromagnetic wave. That's a radio wave. That's light. You're saying, wait, slow down? Fields are properties of space? What does that even mean? It means space itself has structure. Space isn't nothing. Space is a thing, a physical thing, and it has properties. One of those properties is the electromagnetic field. The field exists everywhere, all the time, and its value at each point can change. Think of it like temperature. Temperature is a field. At every point in the room, there's a temperature. You can make a map. This corner is 72 degrees. That corner is 73 degrees. Near the window, it's 70 degrees. The temperature field varies from place to place, and it can change with time. Open the window, cold air comes in, the temperature field changes. The electromagnetic field is like that. At every point in space, there's an electric field value and a magnetic field value, and those values can change. When you wiggle an electron, you change the electric field near that electron. The change propagates outward. The field values at neighboring points change, then the points beyond those, and so on. The disturbance spreads. That spreading disturbance is an electromagnetic wave. But here's the key difference from temperature. The temperature field needs matter, air molecules. Their kinetic energy is the temperature. No molecules, no temperature. But the electromagnetic field doesn't need matter. It exists in vacuum, in completely empty space. The field is a property of space itself, not a property of stuff in space. And now we can finally answer the question, what's waving? The electromagnetic field is waving. At each point in space, the electric field strength oscillates up and down. The magnetic field strength oscillates up and down. The two oscillations are perpendicular to each other and perpendicular to the direction the wave is traveling. The oscillations propagate through space at a fixed speed, 299,792,458 meters per second, the speed of light. That's a radio wave, an oscillation of the electromagnetic field propagating through space. Now let's get concrete. Let's trace exactly what happens when a radio station broadcasts. You've got a transmitter. Inside there's an oscillator, an electronic circuit that generates an alternating current. The current oscillates at a specific frequency. For an FM radio station at 100 MHz, that means the current reverses direction 100 million times per second. This oscillating current feeds into an antenna. The antenna is just a piece of metal, a conductor. Electrons in the metal are free to move. The oscillating current pushes electrons up the antenna, then pulls them back down, up, down, 100 million times per second. The electrons accelerate, up, then down, then up, then down, accelerating charges. And here's the crucial fact. Accelerating charges create electromagnetic radiation, always. This is not optional. This is a fundamental law of electromagnetism. When a charged particle accelerates, it creates a propagating disturbance in the electromagnetic field. That disturbance is a wave, an electromagnetic wave. Why? Because of how fields work. When a charge sits still, it creates a static electric field. The field points radially outward from the charge. It extends to infinity, getting weaker with distance, but always there. That's Coulomb's law, the field of a stationary charge. But when the charge moves, the field has to adjust. The field configuration has to change to reflect the new position of the charge. But the change can't happen instantaneously everywhere. Information can't travel faster than light. The change propagates outward from the charge at the speed of light. The field values at distant points don't know the charge moved yet. They're still pointing to where the charge used to be. Then the information arrives. The field adjusts. If the charge is just moving at constant velocity, the field adjustment is smooth. the field lines stretch and tilt, but there's no wave. But if the charge accelerates, if its velocity changes, the field adjustment creates a kink, a distortion, and that distortion propagates outward. That's the wave. So when you wiggle electrons in the antenna, accelerating them up and down, you create distortions in the electromagnetic field. Those distortions propagate outward as waves. The frequency of the wiggling determines the frequency of the wave. Wiggle at 100 million times per second, you get a 100 megahertz wave. That's FM radio. The wave spreads in all directions, spherically. Every point on the expanding sphere has an oscillating electric field and an oscillating magnetic field. The fields are perpendicular to each other and perpendicular to the direction of propagation. The wave carries energy. The energy came from the transmitter, from the power driving the oscillating current. That energy is now traveling outward in the electromagnetic field. The wave reaches your car. Your car has an antenna, a piece of metal. The oscillating electric field in the wave pushes on electrons in the metal. The electrons move, up when the field points up, down when the field points down. The moving electrons create a current, an oscillating current, at exactly the same frequency as the original broadcast, 100 MHz. Your radio detects that oscillating current. It amplifies it. It processes it. It extracts the information that was encoded in the wave by varying the amplitude or frequency. It feeds that information to a speaker. The speaker vibrates. Sound waves in air. You hear music. But notice what happened. The transmitter didn't send music through the air. The transmitter sent an electromagnetic wave. The wave was just an oscillation of fields. The information about the music was encoded in how the oscillation was modulated, how its properties changed. The receiver decoded that information and recreated the sound. But the wave itself was just fields oscillating. And here's what's extraordinary. Multiple waves can occupy the same space simultaneously without interfering. Right now, dozens of radio stations are broadcasting, hundreds of Wi-Fi networks, thousands of cell phone signals, GPS from satellites. All these waves, all these oscillating fields passing through the same space, through your body at the same time. They don't collide, they don't interfere, they superpose, they add together. At each point in space, the total electric field is the sum of the fields from all the waves. The total magnetic field is the sum of all the magnetic fields. Your radio antenna picks up the sum, but then the radio filters out everything except the frequency you're tuned to. It separates one oscillation from all the others. It extracts the signal from the noise. This is possible because the waves don't interact with each other. They only interact with charges. An electromagnetic wave doesn't push on other electromagnetic waves. It pushes on electrons. So all the waves can pass through each other, occupying the same space, and the only time they matter is when they hit something with charge, like the electrons in your antenna. Now let's go deeper. Let's ask why accelerating charges create waves. What's the mechanism? Why does wiggling an electron disturb the electromagnetic field? The answer comes from Maxwell's equations. 4 equations written down by James Clerk Maxwell in the 1860s that completely describe how electric and magnetic fields behave. These equations tell you how charges create fields, how currents create fields, and crucially, how changing fields create other fields. One of Maxwell's equations says a changing magnetic field creates an electric field. Another says a changing electric field creates a magnetic field. These two facts together create a feedback loop. Change the magnetic field, you get an electric field. That electric field changes, creating a magnetic field. That magnetic field changes, creating an electric field. Back and forth, each field creating the other. The disturbance propagating through space. That's the wave. It's self-sustaining. Once you start it by wiggling a charge, it doesn't need the charge anymore. The wave propagates on its own. The changing electric field creates the magnetic field. The changing magnetic field creates the electric field. They bootstrap each other. They keep each other alive as they travel through space. And Maxwell did something extraordinary. He looked at his equations and realized they predicted a wave. He calculated the speed that waves should travel. The speed depended on 2 constants, the electric permittivity and the magnetic permeability of free space. Both have been measured in completely independent experiments. Maxwell plugged in the numbers. The wave speed came out to 310,740,000 meters per second. That was close to the measured speed of light, too close to be coincidence. Maxwell realized what he'd found. Light is an electromagnetic wave. The same fields that create electric and magnetic forces also propagate as waves, and those waves are light. This was 1865. Nobody had asked for this. Nobody was looking for a theory of light. Maxwell was just trying to unify electricity and magnetism, and out popped the wave equation that predicted electromagnetic waves traveling at the speed of light. He concluded correctly that light must be electromagnetic. This was one of the greatest unifications in physics. Electricity, magnetism, and light, all the same phenomena. And then Henrik Hertz tested it. In 1887, Hertz built an oscillator. He made sparks jump across a gap. The sparks were oscillating currents. He calculated what frequency they should produce. He built a receiver, a loop of wire with a small gap. If electromagnetic waves existed, they should induce a current in the loop. They should make sparks jump across the gap. They did. Hertz detected the waves. He measured their properties. They reflected off metal. They refracted through prisms. They did everything light does. But they had much lower frequency, longer wavelength, radio waves. Hertz had created and detected radio waves. He proved Maxwell was right. Electromagnetic waves exist. Within 20 years, Marconi was sending radio signals across the Atlantic. Within 30 years, radio was everywhere. We'd learned to generate electromagnetic waves, control their frequency, modulate them to carry information, detect them, decode them. An entire technology emerged from understanding one fact: accelerating charges create electromagnetic waves. And all of it, all of radio, all of Wi-Fi, all of wireless communication, it's just applied electromagnetism. It's Maxwell's equations in action. We wiggle charges to create waves. We propagate the waves through space. We detect them by letting them wiggle other charges. That's it. That's the whole thing. But here's what nobody tells you. Here's the part that should completely restructure how you see reality. The electromagnetic field is not just a tool for sending radio signals. The electromagnetic field is fundamental. It's one of the basic fields of nature. And every electromagnetic interaction you've ever experienced is mediated by this field. When you push on a table, you're not touching it. The electrons in your hand and the electrons in the table repel each other electromagnetically. That repulsion is mediated by the electromagnetic field. The field carries the force. You're feeling the field pushing back. When you see something, photons of light hit your retina. Those photons are oscillations of the electromagnetic field. High-frequency oscillations, visible light. The field oscillations cause electrons in your retina to move. The moving electrons trigger chemical reactions. Those reactions send signals to your brain. You see. Vision is electromagnetic field detection. Chemistry is electromagnetic. All of it. Chemical bonds are electromagnetic forces between electrons and nuclei. Reactions are rearrangements of those electromagnetic bonds. The reason molecules have specific shapes, the reason reactions happen at specific rates, the reason you can smell things, taste things, feel textures, all electromagnetic. The electromagnetic field governs all of chemistry. And radio waves, they're just one tiny sliver of the electromagnetic spectrum. One small range of frequencies out of an infinite range. But they're the same field, the same physics. The static electric field around a charged balloon, the magnetic field around a bar magnet, the radio waves from a broadcast tower, the light from the sun, the X-rays from a medical scanner. All of it is the electromagnetic field oscillating at different frequencies or configured in different patterns. There's only one electromagnetic field. It pervades all of space. It exists everywhere, always. And everything you call electromagnetic phenomena is just different configurations of that one field. Now, can we explain why the electromagnetic field exists? Can we tell you why charges create fields? Can we derive Maxwell's equations from something deeper? Yes and no. Quantum electrodynamics, the quantum theory of electromagnetism, gives us a deeper understanding. It tells us the field is made of photons, quantum particles that mediate the electromagnetic force. Virtual photons constantly pop in and out of existence, carrying the force between charges. Real photons are excitations of the field, electromagnetic waves quantized into discrete packets. But QED doesn't explain why the electromagnetic force exists. It describes it more precisely. It gives us better predictions. But it's still a description, not an ultimate explanation. The electromagnetic force is fundamental. It's one of the four basic forces of nature: electromagnetic, gravitational, strong nuclear, weak nuclear. Those are the forces. They're not derived from something simpler. They're the bottom level. We can write down the equations that describe how the electromagnetic field behaves. We can calculate its effects to absurd precision. We can test those predictions and find they match reality exactly. But we can't tell you why those equations are correct. We can't explain why nature chose these rules and not others. The rules just are. They're what we measure. So when you ask what radio waves are, here's the complete answer. Radio waves are oscillations of the electromagnetic field propagating through space at the speed of light, created by accelerating charges, carrying energy and information, detectable by their ability to accelerate other charges. They're the same phenomenon as visible light, just at lower frequency. They exist because the electromagnetic field is fundamental, because changing fields create other fields, because Maxwell's equations describe how fields behave. The field exists everywhere, oscillates everywhere, and those oscillations are what we call electromagnetic radiation. That's not invisible waves carrying music through the air. That's the actual physics, the real mechanism, the fundamental description of what's happening when you turn on a radio. And every time you use Wi-Fi, every time you make a call, every time you listen to the radio, you're manipulating the electromagnetic field. You're creating oscillations, propagating them through space, detecting them at a distance. You're using one of the four fundamental forces of nature to communicate. You're wiggling electrons and detecting the field disturbances those wiggles create billions of times per second. The fact that we can do this, that we can understand electromagnetic fields well enough to encode information in waves and decode it reliably, that we can send signals through walls, through air, through vacuum, that we can talk to spacecraft billions of miles away and receive their responses. That's not mysterious. That's magnificent.